Example 15. We have another Kirchhoff's rules problem. And once again, this is an example to practice your Kirchhoff's loop rule. So you have two resistors, R1 and R2, a current of 1 amp, and an EMF of 18 volts. And then there's this unknown EMF2, this battery here, that we don't know. So as you do with circuit diagrams, you draw out a nice large circuit diagram so you have plenty of room for the labels. And we label everything which has already been done for us, and we go ahead and start the problem. So let's pick a direction that we would like to traverse this loop. We're going to apply the loop theorem. We can't apply the junction rule here because there is no junction at all shown. It's just one single loop. So I'm going to choose this loop here, and we're going to apply Kirchhoff's loop rule, which says the sum of the voltages over a loop is equal to 0. So, and we're going to choose the clockwise loop here. So, as we start here, we see that we go over this resistor. Now remember, the current is going down on this branch as it's shown, going up here and through these resistors in this direction, so it's going counterclockwise. So as we traverse the first resistor, we're going against the water flow current, or sorry, the electric current flow, and so that means that you're essentially going uphill. So we have a positive I times R1. And then we traverse now a second resistor doing the same thing, going uphill, so we have I times R2. And then as we traverse down along here, then we go from the negative to the positive. And as you go up the stairs in your EMF, that means once again you're going uphill. So that is a positive EMF 1. And lastly, as you go over this battery, you're going from the positive to the negative, and in this particular case, you're going downhill. And so then you have a minus EMF 2. And all of these voltages will add up to 0 if you start and you end at the same point by the conservation of energy. So let's now go ahead and plug in our values that we know. We have current, which is 2 amps. We have R1, which is 4 ohms. Plus you have current of 2 amps and resistance of 1 ohm. And then we have EMF of 18 volts, and then minus EMF 2, which is equal to 0. So if we put EMF 2 on the right side, then you'll have 2 times 4, that's 8 volts, plus 2 times 1, which is another 2 volts, plus the 18 volts from the first EMF. And if you add all that up, that will give you 28 volts for EMF 2. And it's pretty relatively straightforward to solve that kind of problem using Kirchhoff's loop rule. If we were to look at the way that we would tackle this problem earlier, you could use this method. You could say the EMF equals I times R equivalent. The equivalent resistance, since you see these two resistors in series, is R1 plus R2. And the EMF, you'd have to realize that since these batteries are in opposite directions, that one is going in the other direction of the other, so you'll have to subtract those two EMFs. So let's assume that EMF 2 is larger because we've assumed the current is going this direction clockwise, counterclockwise, so we'll have EMF 2 minus EMF 1. So this is like a net EMF. And then if you substitute your numbers in here, EMF 2 minus 18 volts times the current of 2 amps times resistance 1, which is 4 ohms, plus 1 ohm, and you will get the same answer. EMF 2 will be 28 volts. So there are really just two ways to do this, but it's just nice to see that you can use Kirchhoff's rules in some of the simplistic problems that you were doing earlier.